Hello everyone, welcome to lecture 3, chapter 3 of mathematical reasoning. In our previous two lectures we looked at a few symbols used in math very frequently. So we looked at the OR symbol, it was a V, an inverted V AND symbol. We looked at for all and there exist symbols. And we did quite a few examples, and in the examples I actually said and again, but I wrote this symbol which is incorrect. This is the symbol for OR, so you should correct that. I have mentioned it in the comment section with proper key times, and you should go and correct that. And this is the symbol for and you can spot the similarity between and intersection symbol and OR and union symbol. If this is confusing to you, union and intersection, then don't worry, we have not gone through this yet. We'll look at this in the set theory chapter in the next lesson. But this is the symbol for and OR. Do take care. Okay, and today we are going to look at the notion of negating something. So negations. So negating or negation is actually an English word. It means proving something otherwise, or I'll write proving otherwise, and if something is true I'll prove it false, and if something is false I'll prove it true. So that's the meaning of proving otherwise. So negating something means just opposing. I'll write, because these are all the meanings. If the students whichever meaning the students find it's interesting to them, you can use it. So opposing some thought, so opposing idea, right? Opposing idea of something. So this is the meaning of negating in English. So in mathematics, what do we do? Say that I come up to you and say that x is greater than 7. One of my students comes up to me and says that he wants to prove me wrong. So what statement does he have to state in order to prove my statement incorrect? So what fact does he have to state in order that will negate my statement, right? So can he say that x is less than 7? Is this the only way of proving me incorrect? Think about it. What if the guy says x is equal to 7? Precisely, x is equal to 7. I stated x is greater than 7. My statement still is incorrect, right? If x were equal to 7. Hence, the negation of p, if someone wants to prove that p is incorrect, the basic minimum fact that he has to state is x is less than, or I'll write it in notation form because we are used to this notation, right? I won't have to spend much time writing. So x is less than or equal to 7. So I'll call this statement, this is a statement, I'll call it not p. So you see the symbol I used? This is the symbol for negation of p, or in short we call it not. So not something. So the negation of x is greater than 7 is actually x is less than or equal to 7, because if either of the, actually this statement, I should have written it in English, x is less than or equal to 7 is actually two statements. X is less than 7 or x is equal to 7. Less than or equal to 7. So if a person makes this statement, this is the exact opposite of p. So now say that I say that if p is true, and I'll if P is true, then what about not P? What will it be? So I say that X is actually greater than 7. Then could it be less than 7 or equal to 7? Well, it's not possible. It cannot be either. So not P turns out to be false. And if P is false, that X is greater than 7 is a false statement, then that means X is not greater than 7, which means that X is less than 7 or X is equal to 7. So our not P statement becomes true. So this is kind of the truth table. I don't like the idea of someone just dictating you a truth table and calling it the definition for negation. That's not how it works. Negation is actually some idea, and the truth table turns out to be just the opposite of the statement P. So pause your video, think about what I have stated here, and then continue. There's one another trick that people often use to negate statements, which I'd like to address now, and why that's not really a trick. I hope you get the idea of this channel day by day, so I'll not want you to use tricks with mathematics. So say that I have a statement Q which says some even integers are prime. How will you negate Q? So what does the statement say? First of all, some even integers, so at least one. So in mathematics we saw this symbol there exists, right? So this also means some or at least one, or there exists. At least one or there exists. So all mean the same in math. When I say some, I actually mean at least one. Even if one integer is prime, some even integers are prime will be a true statement. So now how do I negate this fact? So I'll have to say that even one integer cannot be prime. If that makes sense, right? Think about it slowly. Not Q will be none of the integers can be prime. And another way of putting that would be, because I somehow want to use all integers, I want to state something about all even integers. So all even integers are not prime. You'll soon understand why I used this form rather than writing none of the even integers are prime, because I'll in symbol form, if we write this down, we'll come to that in the next example. This form turns out to be a bit easier to get to, but none of the even integers are prime is a perfectly logical negation for Q. So now what often people teach is, to negate a statement you just add it is not the case that and the statement. So if I have to negate Q, then negation of Q according to my trick will be, it is not the case that Q, and Q is what? It is not the case that, I'll copy paste, right? It is not the case that, I shouldn't have, maybe, yeah, it is not the case that some integers are prime. And then we would simplify this to, it is not the case that some even integers are prime means all even integers are not prime. Ultimately we'll get to the same point, but we cannot define negation using it is not the case that trick. It's because negation is defined in such a way this trick works. it's very important to understand that. Kindly pay attention to this. Do not cut corners. Okay. So we have negated one more statement. Let us look at more examples now. And now I'll give you an example in notation form. So initially what I suggest is, if you're not very comfortable with the notation form, you convert it into plain English and then negate it and then write it down into the notation form. We're not in a hurry now. We're just learning. So B is birds. B is birds. So for all small b belongs to capital B. This is my A statement, A. And what does the B have? So for all birds, B belonging to birds, B has the property that it sings. So what does this mean? Think about it. So it essentially means that all birds sing. If you're not very comfortable with how I got here, you could rewatch my previous lecture. We discussed this in detail. Okay. So all birds sing. So how do I negate this statement? So negation of A is, it is not the case that all birds sing, right? Or what is the, always think of this, what is the basic minimum criteria to prove this A statement guy wrong? So what is the basic minimum thing you'll have to achieve to prove this guy wrong? So if someone says to you all birds sing, to prove him wrong, you'll bring him a bird which does not sing. It'll be proven wrong automatically, right? So there exists a bird. So now can I write it in notation form? There exists a bird belonging to B, a small b belonging to this class of birds, such that not B does not have that property. So here B used to sing, B does not sing. So see how easy it is to convert it from notation for all statements to there exist. And so that's why here I wrote in the previous slide, I wrote it in this form. So this is the reason. Okay. So one more example. This is a nice example. You'll like it. So one of the I usually write down these examples because they are very specific to, each of them are designed to do a specific thing, teach you a specific thing. So I am one of the five people here is a thief. THIEF, thief. So one of the five people here is a thief. Say that I'm calling it P. So what will be not P? So now you should be able to work it out on your own. So pause the video and do try. So I'm saying one of the five people here is a thief. To prove me wrong, what does someone have to do? Even if one of the five people there is a thief, my statement is correct. So if and only if none of the people there are thieves, then my statement is correct. So just for fun, now that we know the negation, just for fun, shall I convert it to a notation form and then negate it? So let me convert this to a notation form. So one of the five people here is a thief means there exists a thief T belonging to the set of thieves. So this is this is a 5 people set, so I'll just call it T5 if you want. You don't need to, but such that T is a thief. So is this okay? Is this notation correct? So there exists a T belonging to T5, which is the set of 5 thieves I have, such that T is a thief. Now if I negate it, what did I say? None of the people here are thieves. Which means for all t belonging to t5, for each and every t in my list, in my lineup, t is not having that property. T is not a thief. So very abstractly, if I have to say, there exists some a belonging to a has some property, a has some property, so a has property, I'll call that property p. Then this is very abstract, so this is just a writing, this is just a summary of whatever we did now. So you can just try to figure it out how I am writing the statement mathematically, and it will work. So there exists a, I'll call this statement alpha. I have used up all alphabets. So there exists a belonging to a such that a has a property p. The negation of alpha would be for all a belonging to a does not have p. So a has not p. So this is very abstract. If you don't understand, then let it be. But pause the video and try to at least pattern match with the previous examples. Okay. So I just checked my time. It's already more than 15 minutes. So I'll stop negations with one more example, and implications we'll study in the next video. Implication is some if-then statements. Really easy stuff, so we'll study it in the next video. So in the previous few examples in a previous lecture, we saw a statement: all parallelograms are trapeziums. And we also looked at the idea of negating. I gave you a brief intro for the idea of negating, proving this thing wrong. So we discussed a slight bit there. So I'll just like to go back and check what's happening. So I'll write it in the notation form first of all, and then I'll negate it. So p in the notation form would be for all p, I cannot, so I'll change the statement name. I'll call it beta. So for all p belonging to the set of parallelograms, right? For all p belonging to parallelograms, what is the property that p has? P is a trapezium. So this is the statement beta is making. Beta is the statement. So what is not beta? So it is not the case that all parallelograms are trapeziums, which means there exists at least one parallelogram which is not a trapezium. So there exists a parallelogram belonging to this set, of course, the set of parallelograms, such that p is not having that property. P is not a trapezium. So is this okay? So again, what often people say is, when you negate a statement, the for all symbol becomes there exists symbol, the there exists symbol becomes for all symbol. But that's a really poor way of putting it, because there's a rich theory behind what happens during negating a statement, right? It's the notion of proving something otherwise. It's the notion of opposing a statement, arguing from the opposite side, right? If the our statement was true, then the negation statement would have been false. If our statement was false, the argument would have been true. So taking all this into consideration, if you just follow the steps, your intuition, automatically your for alls will change to there exists, and there exists will change to for alls. You don't follow the rule that for all changes to there exist, because in some places that may not work. Moreover, you'll be missing out on a lot of intuition that goes behind this. So I think I'll stop here. In the next class, we'll look at yet another important class of symbols we have. Thank you.